Induction heating of the material with temperature-dependent properties. This example is a simulation of a specific problem and at the same time an explanation of a method and application of a tool. We offer this tool for the automation of the simulation process for a wide range of induction heating models where the electromagnetic and thermal properties are temperature-dependent. Let's start from the simple example problem setup. A thermomagnetic billet is heated in round inductor. Both billet and the inductor are long enough so we can neglect the effects at the ends of the billet. We analyze middle section, which may be represented by its slice. So the model geometry is axisymmetric, where the disc-shaped billet is placed inside the inductor. During the heating process, the electrical, magnetic, and thermal properties of the billet change. The task is to find the temperature distribution in the billet during the heating process. In QuickField, you simulate the induction heating process by connecting magnetic and thermal problems in a chain of stages. At each stage, QuickField calculates power distribution in the billet using the AC magnetic problem. Then the power distribution is transferred to the transient heat transfer problem, where the temperature rise is calculated over a short period of time, a stage. Then we transfer the temperature distribution calculated at the end of the previous stage for the calculation of the electromagnetic parameters in the AC magnetic problem on the next stage. QuickField automatically adjusts electrical conductivity based on the temperature, and magnetic permeability is interpolated by scripts in the tool. New power distribution is calculated. Then we pass the new power distribution and temperature distribution to the next stage problem, which simulates the temperature rise during the next stage, and so on. Stage duration should be short enough to consider the temperature, electromagnetic properties to be constant during the stage simulation. The process is controlled by a tool implemented as a Visual Basic for Application script in Microsoft Excel. We publish it on as-is basis with a source code. So if you want to modify our tool, you are welcome to do so. This tool allows to specify the magnetic dependency of the material, the pH curve, and then this tool generates and solves a series of temporal stages for the chain of coupled simulations. Okay, let's start QuickField now and see how to use this tool for the simulation of the simple example we described. First of all, I need to create a C-magnetic problem to find losses. Problem name AC. Next. Problem type is AC magnetics. Frequency is 8000 Hz. Model class is axisymmetric as the billet and the inductor are cylindrical. Length units are millimeters. Finish. On the left you can see the problem pane and the problem tree. And on the right is the geometry model editor window. You should draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I'm going to draw it here from scratch. The billet diameter is 55 millimeters, so I'm going to insert a rectangle with dimensions 10 by 55 millimeters. Insert. The billet and inductor are very long, so in every cross section we have the same current density and temperature distribution. I'm going to simulate only a short slice of the billet with a width of 10 millimeters. Okay. Insert another rectangle with the dimensions 10 by 84 millimeters. Insert. And another 10 by 100 millimeters and another 10 by 110 millimeters. And another one, 10 by 140 millimeters. Insert. Close. Zoom to fit. In axisymmetric problems, the axis of rotation is a horizontal one, and we should draw only the upper half of the cross-section. So switch to insert mode, draw the line along the horizontal axis, switch to select objects mode, select, and hit delete button to delete them. Okay, here you can recognize the billet, the air gap, the fire resistant layer, the thermal insulation, and the inductor. Let's assign labels. To labels, we can distinguish objects and provide material properties. Switch to select objects mode, click the object to select, and type in the label name here. Billet, air, fire resistant, thermal insulation, and the inductor coil. In fact, the magnetic field is distributed not only in the coil and in the billet, but also in the air outside. So I should add the air block above the coil. Switch to select objects mode, click this edge to select, right click, duplicate selection, displacement by 200 millimeters up. Okay, zoom to fit, switch to insert mode and draw the lines here and here. Switch to select objects mode, click this block to select, and this would be the air. Apart from the block labels, you should also assign labels to the boundaries. Click this edge and enter the label name axis. This would be the far away boundary, and these are the symmetry, because to the left and to the right I have the same cross sections of the billet. And I need to assign the label to the billet surface. I will use this label later in thermal problem. And I can delete these edges. Now let's provide physical properties for these labels. Double click the label name in the tree. Magnetic permeability of the air is 1. And magnetic permeability of the fire resistant material is 1. And for the thermal insulation, magnetic permeability is 1. For the coil, which is made of copper, I specify magnetic permeability of copper, which is 1, and the total current corresponding to this short slice of the coil, 700 amperes, which is a root mean square value of the sinusoidal wave. In QuickField, I should specify the magnitude of the sinusoidal wave, which is times square root of 2 more. Okay. For the billet, I specify the BH curve. Here I have the data in the Excel file. Just copy this, click nonlinear, paste it here, close. Electrical conductivity of the steel depends on temperature. Again, here I have the dependency. Click depends on temperature and paste the data here. Close, and the initial temperature is plus 25 degrees Celsius. And the voltage is 0. In axisymmetric problems, any block represents a cylinder with a gap. This is the cylinder, and this is the gap in the cylinder. You can connect the voltage or the current source here. I have specified that the voltage is 0. That means that these parts of the gap are connected. So in fact there is no gap. We have a cylinder without a gap. So that's why we have 0 voltage here. Okay. Now for the edge labels. Far away from the coil, on the inductor, the magnetic field fades to 0, so here I specify 0 magnetic potential. At the axis of rotation, we have 0 magnetic potential because here we have current flowing in one direction, below we have the current flowing in opposite direction, and in the middle, on the axis, we have 0 potential. For the surface, I do not specify any properties because this label I will use in thermal problem. Just click OK, and you see the 0 mark next to the label name. That means that this label doesn't hold any data and doesn't affect the results. And at the symmetry planes, I specify that the tangential component of the magnetic field is 0. Now the geometry model and the physical properties are ready, and we can solve the problem. Before I can start the analysis, I should build the finite element mesh. Just press this button, save all problem files, and solve the problem. Let's take a look at the results. Let's zoom in. I don't like the field picture here. The field lines should be smooth curve, and here I see the sharp corners. Let's solve and refine to get more accurate results. I'm going to do 5 iterations, and I'm not going to limit the mesh size, so I type in 0 here. OK. Now let's take a look at the results. Current density distribution. Let's zoom in. Now much better. Here you can adjust the field picture, change the quantity to draw heat power. I'm going to use the contour tool, draw the contour here, and take a look at the power density distribution along this contour on the XY plot. The exact values you can see in the table: coordinates, current density, draw heat power density. And you can use the contour tool to calculate the integral values. Contour, remove contour, click the body to select integrals. The total current induced in the billet is 942 amperes, and the draw heat power is 2.7 kilowatts. Okay, I have calculated the draw heat power distribution in the billet. Now let's calculate the temperature. To calculate the temperature distribution, I need to create the thermal problem. HT. Next. Problem type is transient heat transfer. Model class is the same, axisymmetric. Length units are millimeters. As you can see, the draw heat power distribution is not uniform. I'm going to pass the draw heat power distribution from magnetic to thermal problem. To be able to pass the data, both problems should be based on the same geometry model file. So here in the geometry, I should type in ac.mod, AC. Next, here I should specify integration time parameters. Let's simulate the temperature rise over 1 second period with the time step of 0.1 second, and the initial temperature is plus 25 degrees Celsius. Finish. The geometry model is the same and the labels are already assigned. In thermal problem, I should provide thermal properties for these labels. I'm not going to calculate the temperature distribution in the air, so I don't specify any properties here. And you see the exclamation mark next to the label name. That means that the field will not be calculated in this block, in the blocks with this label. I'm not interested in the temperature distribution in the coil, nor in the insulation, only in the billet. And for the billet, I shall specify thermal conductivity, which in fact is a function of temperature. Copy this data, nonlinear, and paste it here. The density is 7,860 kilograms per meter cubed, and the specific heat is again a function of temperature. Copy,
nonlinear, paste it here, close. I'm not going to specify the losses here because I will import the losses from the magnetic problem. Okay. On the axis, I specify 0 flux. On the symmetric planes, I specify 0 flux. Far away boundary I do not use in thermal problems, so I don't specify any properties here. And on the surface, I specify the convection boundary condition with the ambient air temperature of plus 25 and the convection coefficient is 5, and the radiation boundary condition. Temperature is 25 and the emissivity coefficient is 0.8. Okay. Now that's all for label properties. Let's add the link. Open problem properties, follow to the links tab. I'm going to import the generated heat from the magnetic problem, which is AC. Let's browse. Here it is. Open, add the link. Okay, we can solve thermal problem now. Solve problem, save modified files. Let's take a look at the results. And here you can see the temperature distribution in the billet after 1 second of heating. Remember that the electromagnetic properties of the slab depends on temperature. QuickField can automatically attenuate electrical conductivity value, and the electrical conductivity will be different in different parts because the temperature distribution is not uniform. But QuickField cannot attenuate the BH curve. As the temperature distribution is not uniform, I'm going to divide the billet into sub-blocks. Each sub-block will have a unique label and unique physical properties. So this way it will become possible to specify different BH curves for a heated block near the surface and for the cold block near the axis of rotation. Okay. Let's open the geometry model. Let's zoom in. This is the billet. I'm going to duplicate this edge. Right click, duplicate selection, displacement by 0.2 millimeters down. Okay. Again, duplicate this edge by 0.5 millimeters down. Duplicate again by 1 millimeter, duplicate again by 2 millimeters down, duplicate again by 5 millimeters down, and duplicate again by 10 millimeters down.
Actually, I have duplicated not only the edge but also its label. So if you click surface, you will see that all these edges have label surface. That was not intentionally, so let's remove the labels from these edges. To select multiple objects at the same time, hold the Ctrl button pressed, and I specify label none. Now only the surface of the slab has the label surface. Okay. Let's zoom in and assign unique label to the subblocks.
Switch to select objects mode. Click. This would be billet 1. This would be billet 2. Billet 3. Billet 4. Billet 5. Billet 6. Billet 7. Okay, now I should provide physical properties for these labels in magnetic and in thermal problem. In the initial moment of time, all these subblocks feature the same physical properties because the temperature distribution is the same, 25 degrees Celsius. So I can copy this and paste it here and do this 7 times. and then just rename this would be billet 2, billet 7, billet 6, billet 5, billet 4, and billet 3, and this would be billet 1. Okay, now I have 7 blocks with these identical properties. Let's solve the problem again to make sure that everything is alright. Build the finite element mesh, solve the problem. Let's take a look at the results. Let's zoom in and calculate some integral values. I'm going to use the contour tool, click and select several blocks to calculate the total power generated in the billet. Remember, it was 2.7 kilowatts. Now it is 2.7 kilowatts. Okay. Next, I should solve the thermal problem. Again, I should copy the label data, copy and paste. Now let's solve thermal problem. Remember, the temperature rise was 150 degrees. Let's see. Open the results. The same 150 degrees. But now in thermal problem I have sub-blocks, so for each sub-block I can calculate the average temperature. Just click the block to select. Integrals, average temperature 149. For this block the average temperature 143. For this block it is 126. 93, 51, 28, 25. Now it's time to explain how to use the tool we created. QuickField features an application programming interface that you can use in various programming languages. We made a tool in Microsoft Excel because it only has a table view. Here is the folder with the simulation files, and this is the Excel file. I already put all the required data here. The thermal problem name is ht.ppm. The label name with the temperature-dependent magnetic properties is billet. In fact, all labels containing the billet at the start will be affected. The stage duration is 1 second and number of stages to do is 10. You can specify the final temperature. If any of the control points reach this temperature, the calculation stops. You can specify up to 3 control points with the labels T1, T2, T3. On the second sheet, you specify the BH curve data. You see, I have different BH curves for different temperatures. And at the temperature above 760 degrees, the magnetic permeability of the steel is 1.1. Okay, let's introduce control points to our geometry model. Open the geometry model. Zoom in. You can create new points by double-clicking any point, or you can use the existing one. I will use these as a control point T1. This would be the control point T2, and this would be the control point T3. There is no physical properties to assign for these labels, so I do not specify any properties here, and I shouldn't specify any properties in magnetic problem as well. Anyway, the geometry model has been modified and the data file has been modified, so I have to solve magnetic and thermal problems again. Solve thermal problem. the same temperature distribution, but now I have 3 control points. At the time when this video is recorded, we have QuickField 7.0 alpha version. It doesn't have the application programming interface in new postprocessor, so I'm going to switch to the old postprocessor. Postprocessor legacy. Let's take a look at the results. This is the old postprocessor, and now I can start the calculations with Excel. You see, a series of problems is generated into a separate folder, and the initial problems are copied in this folder. A chain of problems is generated following this diagram. If you would like to see the code in the Excel, press Alt and F11, Module 1, and here is the code, the macro that starts when you press the Start Continue button. You can request to stop anytime. When the current stage finishes, the script stops. So far it has calculated 4 steps. And on the XY plot you can see the temperature versus time in control points. And you can start continue. Stage number 5 was created, and then stage number 6. Okay, we have calculated 14 steps. We have calculated 4 steps, then we pressed stop, and then we continued and calculated 10 steps more. The last step is 14th, and the temperature in the control point 1 is 735 degrees Celsius. Let's open the problem results. Here it is. Let's check the labels properties. For the billet 1, for this layer, the most heated part, the pH curve reached the point of 0.3 Tesla, and for the most cold part, the pH curve reached the point 0.5 Tesla. So you see the pH curve was automatically attenuated with respect to the block's temperature. This utility is free. You can download it from our website and modify it if needed.
If you search for the induction heating of the material with the temperature-dependent properties on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.